I am David Chan, an electrical engineering major.
I'm Diana Garland, an optical sciences and engineering major, and our team also consisted of Ian Hooks and Ricky Ross, who are both electrical and computer engineering majors, as well as Naomi Yeskas, an information science technology major. This is Project 19073, Opportunistic Radio Signal Positioning and Navigation, or ORSPAN, sponsored by General Dynamics. This poster gives a high-level overview of our project, but we will be going into much more detail with this video. Team 19073 worked very well together. We divided both technical and administrative tasks equally and found throughout the course of the year that our team functioned best when we sped up the traditional 2-week Agile Scrum and met twice a week instead. We kept track of our tasks and code through Jira, Slack, and GitHub. The purpose of the ORSPAN project was to collect radio frequency or RF signals and process those signals using machine learning to distinguish different locations. Signals specific to each location create what's called an RF fingerprint, which allows locations to be differentiated. Once 3 static locations could successfully be determined, our sponsors requested that we also attempt to distinguish between locations while navigating. Our system requirements are as follows. The system shall operate over a specific range of frequencies, 25 MHz to 2700 MHz. The system shall determine between 3 geographic locations using input RF signals. The system shall achieve an accuracy of at least 75%, and the system shall perform on a Linux operating system. The highlighted boxes on this slide show the critical components for our use case, which is positioning a user's location. As built, our system is a k-nearest neighbor or KNN algorithm that fulfills all system requirements. The system block diagram is shown here for reference. This algorithm also fulfills all system requirements for locations about a half a mile apart, which completes our navigation stretch goal.
The first step in this project was to use the setup shown in the system design drawing to collect data. We first needed to attain a software-defined radio, or SDR, and an antenna. To do so, we conducted a trace study of the SDRs and antennas. We chose to purchase the line SDR due to the price and amount of features, and we also chose to purchase 2 disco antennas, which were chosen due to the large bandwidth. Here is a picture of the actual GNURadio software that was used to collect data. To test the noise of the SDR, as well as verify that we're operating within the bandwidth, we put the SDR in an anechoic chamber. The SDR ports were terminated to eliminate external noise, and we directly injected a signal. Looking at these 2 pictures, some of the spurs do occur in the SDR, which suggests the datasets could be biased between these SDRs. To counteract this, we established a procedure to efficiently and consistently collect data to input to our algorithms. These were the 3 locations that we chose to collect static data, and here's an example of the data capture in GNURadio. We started with 2 different datasets in each location, one for training the algorithm, one for testing the algorithm. The spectrograms of these locations from GNURadio are shown here. These spectrograms give an idea of the uniqueness of each dataset. Then we moved on to our navigation stretch goal. This tested our algorithm's performance in a more realistic scenario. To collect data in this case, we attached a UHF antenna on the top of a moving vehicle.
Once we had obtained data, a machine learning algorithm needed to process that data and output the location corresponding to each RF fingerprint. We closely considered 4 different machine learning techniques. The first was a support vector machine, or SVM. This algorithm uses linear classification to draw vectors between different groups of data. Although this algorithm is accurate in high-dimensional spaces, it is computationally inefficient, meaning it takes a long time to process lots of data. Since we wanted to pursue our navigation stretch goal, this algorithm was not explored past the first semester. Next, a multilayer perceptron, or MLP, was built. MLPs are the most generic form of a multi-layered neural network, and thus have a wide range of applications. They use backpropagation to calculate the gradient of an error function using weights of the neural network. This algorithm was especially promising due to its potential to fulfill our navigation stretch goal. However, we were initially hesitant to explore this algorithm since it required a significant amount of development time. The third algorithm we explored was a convolutional neural network, or CNN. A CNN is a type of multilayer perceptron that functions through image classification. This required an input of a spectrogram. Unfortunately, the accuracy of this model was significantly lower than the MLP and KNN algorithms. The fourth and ultimately most successful algorithm we explored was a k-nearest neighbor, or KNN. The KNN uses a distance calculation to classify data. This classification technique makes implementing a multi-class problem, or in other words, multiple locations, relatively simple. However, we were originally concerned about the effect that dimensionality could have had on prediction accuracy. After evaluation of these algorithms, we ranked them based on performance, schedule, and cost. The KNN was chosen for our minimum viable product, which we delivered at the end of the first semester. The SVM was no longer explored after the first semester. However, an MLP and CNN were built and tested in addition to the KNN.
At the end of the year, our best algorithm was the KNN. As mentioned before, all the system requirements were met, and verified by this algorithm. Our requirements were verified through inspection and tests. The range and operating system were simply verified by confirming that the algorithm worked within the appropriate bandwidth and that the algorithm ran on a Linux operating system, which we coded in Python through Anaconda. The ability of the algorithm to determine between 3 different locations was confirmed by testing the algorithm with test data. And finally, the accuracy of the algorithm was confirmed through training and testing. We achieved over 75% accuracy even with our stretch goal data. First, we have the MLP results. The algorithm did have an accuracy of 81%. However, the computation time was significant, which limited our ability to thoroughly evaluate the algorithm. We wanted to validate our results by plotting a confusion matrix, which is shown here. The diagonal matrix highlighted in blue are positive results that are true, while values off the diagonal are false positives or true negatives, which are not desired in our algorithm. Next, we had the CNN results. We obtained 72 PSD or power spectral density images to input to this algorithm. However, this algorithm only achieved the accuracy of 50% and the confusion matrix performance was not great. Here is a simple high-level block diagram for our KNN. We use the magnitude of FFT and other signal features and pass them to PCA to reduce our computation time. The scatter plots from the KNN show 3 different locations, where green, blue, and red each represent 1 location. This algorithm had an accuracy of 83%, making it our best performing algorithm.
Throughout this project, we have learned a variety of lessons. The first was essentially time management. Data collection took much more time than we originally expected, so we had to divide up tasks accordingly. We also lost one of our team members during the second semester, so we again had to restructure our tasks to account for that. Finally, in our algorithm trade study, although, for example, the support vector machine seemed to be the second best option, it ended up being significantly slower than the other algorithms. This taught us that the speed of the algorithms should probably have been included in our performance evaluation for the trade study. We also learned some more technical lessons this year. Some of our algorithms required a significant amount of data collection, which none of us had really dealt with before. So we had to establish consistent techniques for data collection and handling. Additionally, we had to learn a lot of machine learning concepts that many of us were unfamiliar with. We spent a bunch of time researching these concepts and directing questions to our sponsors. Finally, our software version control became somewhat confusing due to our concurrent use of GitHub, Slack, and Jira. Delegating code to only be uploaded to GitHub, conducting other discussions through Slack, and assigning tasks through Jira was beneficial for our productivity. These are the final remaining deliverables in this project. This design day video, as well as the poster, will be submitted to our mentor, sponsor, and judges. Our final KNN algorithm, including verification of all system requirements, will be delivered digitally to our sponsors. And our final documentation will be digitally distributed by the end of the semester.